We are live.
We go.
Let me just admit all of them in. Okay, good morning, good evening, good afternoon, everyone, wherever you are. Welcome to this seminar about covariance-based structure question modeling using Smart PLS. This seminar is organized by Bahçeşehir Cyprus University in North Cyprus. It's fantastic to
We lost your audio. It shows you have your microphone muted right now.
I think now we are here. We are back.
There you go.
Yeah, so it's fantastic to see people all around the world has registered for this seminar, which make it.
It muted you again.
Now it should be fine, I think.
There we go.
Yeah, so it's really fantastic to see all of you here around here. Before we start this seminar and dive deeper in the world of covariance-based structure question modeling, here's a quick reminder for all participants. Please feel free to ask any question if you have by using Q&A box. Due to the time limitation, we may not be able to answer all your questions. We will do our best to take the most common questions. And I'm excited to inform you that this seminar is sponsored by Smart PLS as a token of appreciation for attending this seminar. All participants will get an access code to use the 2 months for free, the professional version of Smart PLS. We will share the code with you during the seminar. Now let's turn our attention to the start of this seminar. It's a pleasure. It's pleasure to welcome you, Professor James Gaskin. A big thanks for accepting my invitation and being with us here. It's genuinely honored to have you share your knowledge, your expertise about covariance-based with us. I will stop here. I will now give the floor to my colleague, Dr. Bildan, who is going to introduce or give a background about our distinguished Professor James Gaskin. The floor is yours, Dr. Bildan.
Thank you, Dr. Ahmed, for this welcoming greeting. And just after our special thanks to our Bahçeşehir Cyprus University, I also want to thank especially you for making this event real. Without you, it would not be possible. And yes, esteemed colleagues and scholars, it's my pleasure to welcome you all to our webinar. So allow me to introduce an influential figure, today's presenter, Professor James Gaskin. He's a professor of information systems at Brigham Young University in Utah. He earns his PhD in MIS from Case Western Reserve University. With over 200 peer-reviewed published papers across 18 disciplines, he has made a significant impact in academia. His work has been featured in 55 respected journals and conferences. Some of these journals are Journal of Business Research, Computers in Human Behavior, and MIS Quarterly. Additionally, he holds prestigious editorial positions. 1 second, can you please mute your microphone? Oh, thank you. Sorry, this can happen. Now I can hear myself. Yes, his work has been featured in 55 respected journals and conferences. Some of these journals are Journal of Business Research, Computers in Human Behavior, and MIS Quarterly. Additionally, he holds prestigious editorial positions. His research is also very highly relevant for today's world. His focus is on augmented reality, human-computer interaction, and human-AI collaboration. On individual level, his attention is on mental health, while on organizational level, he is interested in sustainable development goals. But there's more about him. Outside of his own field, James Gaskin is widely recognized for his dedication to knowledge sharing. We all know his well-known platform StatWiki and related YouTube channel Gaskination. Through these channels, he has reached millions worldwide with his video tutorials on statistics. Additionally, he provides guidance to scholars and practitioners globally, while offering his insights and support through his structural equation modeling videos and workshops. As you can see, these roles highlight his commitment to advancing knowledge within his own field and his dedication to scholarly excellence. So we are very lucky to have him today with us, and I am sure we are all eager to explore the insight he will share with us today. So if you are ready, I'd like to turn the floor over to him. Yes, Professor Gaskin, the floor is yours. Welcome.
Thanks. Thank you both for inviting me. When you guys invited me, I thought there would be like 30 people or something. So this will be fun. Thank you everybody for coming. I'm very surprised and pleased that everybody could come. So I also was looking at the schedule. There we go. I got muted automatically. That was fun. I initially thought the agenda was all of Smart PLS, and I looked at it yesterday and I was like, oh no, it's just covariance-based. So we'll see how long we go. Covariance-based SEM in PLS, it's not a lot of content yet. They're still building it up. And so I have plenty of things we can go over, and there are a few things in the general Smart PLS we can go over as well. I'll focus on covariance-based features. I'll assume that a good portion of you have used Smart PLS before. I'm also going to assume that you're not following along with me step for step. That wouldn't work in a group this large. So I'll go faster than I would if you were following along. I won't go too fast because I'll explain things as we go. And as Ahmad said, if you have questions as I'm going through, even though there are so many of you, it's okay. Just put a question in the Q&A. And if I don't see it, Ahmad or Vildan will see it and they'll notify me. And I'll try to answer every question that we get. And hopefully I'll know the answers. Statistics, it's a big field. So, you know, maybe I don't know. I know a lot about PLS, a lot about SEM in general, but there are things I don't know. So hopefully I'll be able to answer your questions. With that, I will open up, let's see, I'll do a screen share. Let's see, I want to share this screen. I want to share all my screen, window, screen. There we go, screen. I don't use Microsoft Teams, so this is new to me. Here we go. I think I am sharing something. Vildan, can you tell me, do you see the like the SEM model, the CFA here? Excellent. Okay, so you can see my screen. Yay. All right. So there are a bunch of things we can do in Smart PLS with CB-SEM features. For those who are, this is like totally new, quick overview. So SEM obviously is how you relate latent factors together and see if they hold up validly, if they measure things properly. If they and then also you can relate them structurally. That is, you can see how one construct affects some other construct in a latent manner, which is really cool. Something you can't do with just basic regressions. Now there are two camps here. There's the PLS, partial least squares camp, and the CB, covariance-based camp, and they have been not at war, but on different sides of SEM for a very long time, for decades. And until recently, you could not do both in the same software. Sort of. They're actually, you could do it in R, but nobody wants to do that because R stinks. But you could not do it in a user-friendly software until now. So Smart PLS recently came out with a covariance-based, I don't want to call it a partition, but like a side of the Smart PLS software is devoted to covariance-based structural equation modeling, which is awesome because the biggest argument against using partial least squares to this point is that you couldn't do model fit. You couldn't check the goodness of your model and whether the model was specified correctly. And so people would just discount partial least squares because you couldn't test model fit, so you never knew if your model was good enough. That was a gross understatement and simplification of the arguments being made, and also it's a short-sighted argument. But that was essentially the argument. But now in SmartPLS, you can check model fit in a covariance-based maximum likelihood environment. So I'm going to show you some of the things you can do. And as Ahmad said, you're going to get access to SmartPLS. If you don't have it already, you'll get a free 2-month pro license, fully featured, no limitations for 2 months, just to try it out and see if it all works. And I know this is very small. I couldn't increase the resolution on this window, but I have a zoom in tool that I'll use from time to time. Hopefully that zoom in works and you can see what I'm doing here. So here we go. The first thing I want to show you is many of you probably are familiar with AMOS. It's probably the more popular covariance-based SEM tool. And SmartPLS made it easy for you to take your old AMOS models and import them into SmartPLS. In fact, I discontinued AMOS. I have not installed it on my current laptop. It is not currently installed. I just abandoned it because I see no point anymore now that SmartPLS has covariance-based methods. And so I had to go find an old model like on my Google Drive just to demonstrate for this workshop. I still haven't installed AMOS on this laptop. So here is, let me show you from before. Here is a very complex confirmatory factor analysis, a very complex latent measurement model from AMOS. This is what it would look like. Lots going on here, lots of variables, lots of indicators and lots going on, lots of parameters, huge chi-square. And so you can import something like this into SmartPLS, and I'll show you how to do that as we go through. So for those who've never used SmartPLS, which is I'm guessing about half of you, this is the interface. And you start a new project by clicking the new project button, calling it something. We'll just call this CB SEM PLS workshop or something like that. And hit create. And what this does is it creates a new project folder over here. And we can import data or create a model. I'm going to go up here to Files. And there's an option, you can zoom in here. There's an option to import an SPSS AMOS file. So I'll click on that and go over to my PLS workshop. And I know you can't, there we go. Here is an AMW file. For those who are familiar with AMOS, the model files are called .amw. And I'll just open that and zoom out. Here we go. It's going to ask me, where do I want to put that? I want to put that in this current workshop folder. And what do I want to call it? I would just call it, CFA initial. That works. It just guessed that from the original file name. I'll hit apply, and it starts thinking, and it produces this very complex model. Now, it's kind of squished here. If you want to zoom out, I guess here's the interface. You guys, if you haven't used SmartPLS before, this is the interface. And there are a few features we can take a look at here. First, the canvas area for the model. And then you can zoom in and out with this slider down here. I'm going to zoom out for a sec so I can adjust things. Just pull that down. And it has some auto snapping alignment, which is nice. Ooh, there's a lot going on here. Maybe I should have picked a smaller model. Oh well. This will show that it's truly capable of recreating complex AMOS models. Oh boy, need more space. But one thing I like about SmartPLS is it's pretty user-friendly. You can just drag and drop stuff, which is nice. Some other SEM software, you can't do that. You can't just click on something and move it, which is weird. Let's see, almost there. Control A, pull that down, and then Let me show you some stuff with the interface. You'll notice all of these things are aligned left. If you wanted to align them in a different orientation, there are some arrows over here. You can align them up, down, right, as you click those buttons. I'll keep them left for now. And you can mess with all the colors and design and stuff, but I'm not going to mess with that. You can also, let me zoom in again. You can see over here on the left, we don't have any data, which is a problem. So let's go import some data. So I'm going to save this, go back and import data. And I'll just go get the data that I have for this workshop. By the way, I suppose, Vildan or Ahmad, if you want, I can give you guys access to this data and my Amos model and everything afterwards. Okay, let's see. Let me go grab this data, open. And I'll show you this. So here's the data import dialog. And I'm not going to go through all the details. I have videos on all the details here. But essentially, it reads your data. And SmartPLS 4 is really good about reading data. If you've used SmartPLS 3 or 2 prior versions, it was terrible. It was just terrible at reading data. And you could only use like a .dat file. But now you can use .sav for SPSS or a CSV for Excel. Or .dat if you really want to. And it reads your file, it guesses what kind of scale it's on, it checks the observed minimum and maximums, and you can uncheck them if you don't want to bring in every variable. You can change what kind of scale it's on if you really want. And you can even apply a missing marker. So some other software you may have used allows you to specify when you have a marking value as missing. So if your data has missing values in it, some software doesn't allow you to have missing cells in your data set. It doesn't handle it well. And so you have to apply a missing marker like -999 or something like that. And that implies that value is not -999, it's just missing. And so you could, if you had a missing marker in here, you could tell it what it was. I don't have a missing marker in this data set, so I'm not going to apply that. Though it did find 242 empty values. So not part of this workshop, but just so you know, that is an option. I'm just going to keep all the defaults, click import. There are reasons to change those defaults, but we won't talk about them today. It does a quick analysis of your data. Here are all the variables and how many are missing on each of those, and means, medians, mins, maxes, and kurtosis, skewness, things like that. And so you can see if there are any issues with your data. We're not going to do that today. Again, that's not the focus of this workshop. We're just going to look at the covariance-based features of SmartPLS. So one other thing I guess I should mention here is if you're using the PLS side, not the covariance-based side, you can add groups and you can do a multi-group analysis. Again, not yet in the covariance-based side, though that is coming, I've been told. But for now, we have to use the PLS side of SmartPLS to do multi-group analysis. I'll just hit back. And you know what I need to do? I'm going to see if I can see the Q&A window. I don't think I can. I just want to make sure I'm not missing anything. Let's see if I put this over here. Haha, sorry, I'm just rearranging my own windows. Looks like we're good. No questions yet. All right. Although there is something in chat, but I won't manage that. I'll just keep my Q&A window open. Okay, back to this. Sorry, logistics. So we now have data, and we know we have data because it's over here, and we know the data is okay to use because it's green. If there was some error in our data set that wouldn't allow us to use it properly, this would be red or orange, but it's green, so it's good, and we can move forward. So I'm just going to reopen that CFA initial model. Just double click it. And you can see on the left, we now see all of the variables listed. And the MET just means a metric. If they were ordinal, it would say ORD. And there are all the variables, and we can see that the model itself is ready to run because it's all blue. SmartPLS uses a color coding system where blue and green are good and red and orange are bad. And so if things are blue, you're good to go. And we're blue, yay. Couple things real quick before we run this. For those not as familiar with covariance-based, or who have maybe used PLS but not covariance-based, notice there are some differences here between those two types of models. In this model, in covariance-based methods, there's an assumption of a constraint per latent factor. And so this equals 1 just means that this path right here on this indicator has been constrained to 1. And the reasoning behind that, the math behind that, don't worry about it. It's just required for this algorithm to run. It is a necessary parameter to be constrained. On the left over here, we have these circles. These are all error or residual variables. Anything being predicted with regressions requires error. There is error associated with prediction. And these are predictions happening here. It's the latent factor as a cluster of sorts, predicting these indicators. And because there's prediction going on, we need error. So that's what those are. These are correlation or covariance arrows. And these blue ones are the latent factors. These items are the indicators, the actual variables from our data set. So there's your quick overview. If ever you wanted to change anything on here, you could double click it and change those values. Okay, let me zoom out. We are ready to run this. This was automatically produced for us, which is so nice. We didn't have to build that. I'll show you how to build one in a minute, but this was just automatically produced for us. What you'll do if you want to run this is you hit calculate, and right now there are only 2 algorithms you can run in covariance-based. If we switch over to the PLS or over to process, there's a ton you can do. But in the covariance-based side, there's just 2 things right now, and we'll look at the CBM algorithm or CBSEM algorithm first. No bootstrapping. So this just runs your typical maximum likelihood covariance-based SEM. Nothing fancy here. It is just the defaults you would see in Amos or Lizerl or something like that. So I'm just going to keep all the defaults. And if you want to know what each one of these things means, you can always click on it. So if you click on anything, it tells you what it is. And if you're still not sure what it is, you can always click on more info and it will take you to the website and explain more. It's pretty nice about SmartPLS. And so I'll just keep these basics, these defaults. I'm going to hit start calculation. And one thing I like about SmartPLS is it uses parallel processing to run its algorithms. And so it's very fast compared to some of the older software like Amos, which is still sort of founded in the 90s logic of CPUs. Okay, so that ran, and you'll notice one thing right off the bat, which is these values seem to be like Haywood cases, right? They're just unstandardized. And so if you want to view the standardized estimates, it's down here in the bottom left, at least for now. They keep changing the interface. So we'll see where it is. We'll see where it is in a month. But in PLS, they refer to the outer model as this stuff outside of the latent factor relationships. So it's the indicator estimates. Those are the outer model. So if I want, I can change that to standardized. And when I do that, you'll see they all change to a standardized view between plus and minus 1. And we can look at correlations. There are lots of options here. There is an option to correlate error terms, which I strongly disagree with. So, but if you had error terms correlated, then you could view those as well. But we'll just keep it here on only intermodel correlations. Those are the correlations between the latent factors. And then we'll keep all of that as defaults. Okay. There's, I guess the last thing here is inside of the latent factors, if you were doing any prediction, you could see the R-square. Since we're not doing any prediction right now, I'd like to see the AVE inside the latent factors. And so we now see inside of each latent factor, its average variance extracted. That's kind of cool. You can just see it right off, right in the model. So visually, this is very easy to use. The AVE is right on there. You can see the standardized loadings, and you can see, so then with just a glance at your model, you can see this is a valid factor. If you were to hover over it like I'm doing now, it also brings up the Cronbach's alpha and the composite reliability. And so you can see that factor is good. Come down to this factor. Hey, that factor is good. Let's see this factor. It's also good. What is good? Sorry, I'm making assumptions here. If I don't know how much to explain because of the audience. With almost 300 or however many there are, there's going to be a lot of variance in current understanding of SEM. So I'll do my best to balance real quick. So a latent factor like playful or anxiety, these are latent factors that are measured through these survey questions right here. And a higher number here, closer to 1, is typically better. Above 0.7 is great. Above 0.5 is tolerable. And you want these to average out above 0.7. Oh, something beeped. I wonder if that was a question. Again, I'm not familiar with Teams, so I don't know. Oh, someone's waiting in the lobby. That's what that was. Sorry, I'll let them take that. Okay. Anyway, back to here. Sorry, new to Teams. So you want your latent factor to measure things well, and or to be measured well, excuse me. And so an AVE, the average variance extracted, is something like the squared average of these guys, these indicator loadings here. And you want that to be above 0.5, which would imply that more of the variance in that latent factor is explained by its indicators than by error. And so above 0.5 is good here. With Cronbach's alpha, you want that above 0.7. Same with composite reliability, you want that above 0.7. And so with that in mind, AVE above 0.5, and then the others above 0.7, and then these over here averaging out above 0.7, we're looking pretty good. These are valid factors. And we can just scroll down, looks like we're looking pretty good. These all look really good. For those who see these values on the residuals, these are variance values. You just want something in control. You want a variance value that's not wild and sort of an outlier when it comes to all the other variance values. So we can see here all these variance values are roughly the same. They're all modest numbers, all less than 1. That's what we're looking for. It's just nothing wild and crazy. That's good. With correlations, these values can be whatever between plus and minus 1. If it gets above 0.8, then you start to wonder if you are measuring the same thing twice. But there's no like guideline here for what these correlation values should be. That really depends on your theory. Okay, so that's a quick overview of the CFA. We can also draw a causal model, which we'll do in a moment. But let me show you a few more cool features about the model, about the covariance-based side. So over on the left, and this is common for both covariance-based and PLS side, you'll see the output options. And we have all this stuff. I'm going to focus on the quality criteria here. So we now have model fit in PLS. If I zoom out here, whoop, then we get to see all this model fit stuff. Let me zoom in just a little bit more. Here we go. Lots and lots of measures here. The kind of standard ones that most people report are, of course, the chi-square. There's no threshold for that. That's dependent upon the model complexity and sample size. The p-value, which should be not significant, but again, that's very sensitive to model complexity and sample size, so most people don't worry about that. The chi-square over the degrees of freedom, which should be between 1 and 5. And looks like we have a good value there. And again, we're looking at the, sorry, I didn't say, we're looking at the estimated model. Whoops, I shouldn't have sorted that. Let me see if I can reset that. There we go. We're looking at the estimated model. This is the model we proposed, the model we drew. The null model is a model without all the parameters specified, without any arrows. Okay, back to here. Let's see. The RMSEA is very common to report, and you want that less than 0.06, ideally, although you can get away with less than 0.1. It's green. I don't know if you can see that green across the Zoom share, but it is green, which means it's good. And then a lot of people still report the GFI, although that is an old measure. I would hesitate to report that. Same with AGFI and PGFI. The SRMR is a good, robust measure, and it should be less than 0.08. It's also green here, which is good. The NFI is pretty sensitive, so that is subsumed by the CFI, same with TLI. But the CFI is considered the more robust measure, less sensitive to sample size, and that should be above 0.9, although if you want to be ideal, it'd be above 0.95, but above 0.9 is fine. And then AIC and BIC are old measures of model fit, and they're a little bit like chi-square, where as they drop, you are having a better fit, more or less. That's a pretty broad simplification of what it is, but there that is. Okay, let's move off of model fit. I haven't talked about what happens if you have bad model fit. Real quick, model fit overview. Model fit is when you take the covariance matrix that is built into the data set. So you have a data set, all the variables are related in some way. Like if you were to throw them all in a correlation analysis, they'd all be related. And so if you were to take the variables from your model, the ones that we included over here in this model, and throw them all into a correlation analysis, and then compare that to the correlations we've specified, which is that all of these items are correlated, and then all of the anxiety items are correlated, and then all of the playful items are correlated. So we've sort of constrained the model to be a certain way. It's the proposed model or the estimated model. There's a covariance matrix associated with that model. And so if we were to compare those two covariance matrices, the one that is observed built into the data that implies no constraints, and then the one where we've constrained some things, this model, and we were to subtract one from the other, we'd get a chi-square. That is the chi-square. And so the more different our model is from the observed model, the worse the fit. Our model doesn't fit the data. And so it's poor fitted. We don't have goodness of fit. And so our chi-square inflates and everything else is bad. All the model fit is bad. And so our model isn't specified correctly. I put that in quotes because we assume there's some baseline truth. But yeah, the further your proposed model is from the observed model, the bigger the chi-square, the worse the model fit, because your model doesn't fit the data. There we go. There's an overview of model fit. Hopefully that made a little bit of sense. Let's see. But if you didn't have good model fit, sorry, that's what I was getting at. If you didn't have good model fit, if those values were all red, well, that means that the indicators you've included here as a grouping for a latent factor, they don't really belong together. They're more related to other indicators over here, not to themselves. And so the within factor correlations are poor. That's what that model fit means. And there are stronger correlations with those indicators with other factors items than with their own items. That's what that is. So you'd have to go mess with that. In fact, the best way to figure that out is probably an EFA, an exploratory factor analysis, which you can do, just not in the covariance-based side of PLS. You can do it over in PLS. Maybe I'll show you that in a moment if we have time. Okay, there's model fit. Once you've established model fit, then you need to establish, so that's sort of a global measure of quality is model fit. You need to now move into more local measures of quality, which would be a measure of whether usefulness, this latent factor here, has quality, has validity, and whether anxiety has validity itself. And to do that, you come over here to the left and do construct reliability and validity. Now, for those of you who have used other software, I'm just going to say it right now. You're welcome. This software actually gives you useful output. I don't know what it is with SEM and statistics software. It's the worst. Like all of it out there is just, it's terrible when it comes to output. I've used a bunch of them and they don't give you the tables you want. They give you a bunch of output and then you got to like calculate the tables you want and make do all the math and all the interpretation and organization. And it's just, it takes forever. And all they had to do, all the developers had to do was write like 2 more modules, like another couple hours of work. And it would have saved hundreds of thousands of hours of work for the world. But they didn't. So, but Smart PLS did. They produce the tables we actually want. They produce interpretations for us. It's just awesome. So let's go over here to construct reliability and validity. We can see the Cronbach's alphas, which are calculated for us. Hallelujah. And they're interpreted for us. Anything above 0.7 is color-coded green. Anything below 0.7 is color-coded red. There are reasons for why the social desirability bias, negative and positive, are red. They are instrumental variables here for detecting method bias and other things. And so I don't actually anticipate them to be highly valid. I'm not too worried about those. If we go over here to the right, composite reliability, like I said before, should be above 0.7 and the AVE above 0.5. So we're doing great, again, except for these two here, which I didn't expect to be highly valid. And then if we go over to discriminant validity, so that was convergent validity and reliability is what we just looked at. And that just means, sorry, I need to back up and always explain. Convergent validity and reliability mean that you have measured a single thing with each latent factor. So over here, back to here, this set of items for usefulness, let me zoom in again. This set of 1, 2, 3, 4, 5, 6, 7 items for usefulness have consistently, that is reliability, and validly, convergent validity, measured the same thing, measured one thing, which we have theorized is usefulness, the construct. So that's what those two measures mean. Now we also have to see if we have measured different things, distinct things, with each of these sets of measures, and that is discriminant validity, which is to say, is usefulness different from anxiety, and is that different from playfulness? And so we see that in the discriminant validity section over here on the left. And there are two different ways you measure that in SmartPLS. One is with a heterotrait monotrait HTMT ratio matrix. And you can see this is all green because we're looking at values less than 0.85. And anything less than 0.85 is considered distinct. So if we were to look at, here's decision, I just sorted it. Whoops, let me go back and back. There we go. If we look at decision quality and follow that matrix value down to playfulness, here's playfulness, we can see that, sorry, that's really hard to read. I'm going to click on the one below it. But here it is, playfulness and decision quality. They have a HTMT of 269, which is to say that they, it's a little bit like a correlation where the higher the value, the more variance they share. And if they share too much variance, you start to worry that they might be the same thing. And so this is saying that playfulness and decision quality don't share a ton of variance. They are truly distinct. The one you might have to worry about is this one, 0.713, decision quality and information acquisition. These have a 0.713, much higher, but still not beyond that target, that recommended threshold of 0.85. So these are still clearly distinct constructs, which means the items for information acquisition and the items for decision quality, they're measuring two different things. If you were to plot them in a factor analysis, they would cluster in separate locations. So we're good. The other way to look at that is through the Fornell-Larker criterion. I see a question from Abdelatif, and his question is, hi James, do we have modification indices in SmartPLS like in AMOS? And the answer is currently no, but that is definitely on the feature request list that I've submitted to SmartPLS. They do plan to create modification indices. For those who don't know what modification indices are, there is in covariance-based methods a way to identify unspecified parameters which, if you specified them, would improve model fit. So when you subtract the proposed matrix from the observed matrix, there are gaps that create big differences. It can identify the correlations, more or less, that are missing that have a big effect on the chi-square. And that is a modification index. And so it'll raise the big ones to the top. And then if you were to address those big gaps between the observed and proposed matrices by adding another line is what it gets down to. You add another line in your model. And you can address that, add another line, and then it fixes your model fit. It improves the model fit by suppressing or deflating the chi-square. So, sorry, that was a long answer. Short answer, no, not currently, but it's coming. Okay, good question. And I hope they fully fill out the features of covariance-based side of SmartPLS soon, and I know they plan to. There's the Fornell-Larker criterion, for those who are wondering how that's spelled, there it is, Fornell-Larker criterion. And this is the traditional method in covariance-based methods for establishing discriminant validity. It is just a correlation matrix, and then on the diagonal, you have the square root of the AVE, the average variance extracted. And you want that square root value on the diagonal to be greater than any correlation with another factor. What that implies is that the items of that factor, let's take a look at decision quality here. The items of decision quality are explain the variance in each other better than other items explain the variance in those items of decision quality. So here's information acquisition's correlation with decision quality. It's a high correlation, but it's still less than the square root of the AVE right there, which implies that decision quality items better explain decision quality than information acquisition items, meaning these are two distinct constructs that are measuring two different things. Now, if we did have a violation here, it would be in red, and it would imply that there is too much overlap between those two sets of items. It's kind of hard to detect how to fix that in the covariance-based side of Smart PLS, though there is a way to do it in the PLS side, which, again, if I have time, I will show you that. We have about 1 hour left before we, about an hour left. So we'll see how far we get. Okay. I just have another meeting on the other side of campus in an hour and 20 minutes. So here we go. So we're good on discriminant validity. If we weren't good, what we'd have to do is find the items that, let's use this example again, decision quality, shouldn't have sorted it, decision quality and information acquisition. What we'd have to do is find the items from information acquisition that are highly correlated with the items from decision quality, and either omit one of them, like drop it out of the model to see how that affects it, or drop one from decision quality to see how that affects it, see if it separates those two in the correlations. And there's an easy way to do that on the Smart PLS side, or on the PLS side of Smart PLS. Okay, well, that's validities and reliabilities. Let's go back to this model here. I think next I can just show you briefly how to build a model. And actually, I'm going to show you how to, I'll show you how to build a model, and then we'll do a structural model, because this has just been measurement model to this point. So let's create a structural model. Let me save this. Yeah.
Professor, we cannot see your screen. I think it's frozen.
Oh no, the screen's frozen. Okay, I can reconnect. Let's see. Let me disconnect my screen. Stop sharing. There we go. I've stopped sharing, and now let me try to share again. This one. There we go. Okay. Let's see. Can you see my mouse moving? Hopefully. Okay.
It's moving now. It's an empty screen now.
Good. Okay. So what I'm going to do, save this. Let me save this as CFA. Oh, this is the report. I don't need to save the report. I'll just hit back and save this and go back. And I'm going to create a new model. So we can keep this measurement model. And if we want, I can just duplicate it, which is easiest, probably. In fact, I'll just do that. Or we can create a new model, which I should probably show you how to create a new model. I'll do that. Let me right-click and say New Model. And there are different types of models we can include. Right now, I'll do the CBSEM model, because that's the focus of this workshop. And it wants me to name it. So I'll just call this, CBSEM. But I'm going to call this causal model, or structural. That's probably the right way to say it.
It's still blank.
Are you not seeing it?
No. And the others cannot see also.
Oh, no. Okay.
I don't know why.
It says my internet connection is good. I will stop sharing again just to see if this helps. Let's see, stop sharing. Okay. And then I'll start sharing again. Let's see, share. And make sure I'm adding the right. Oh, I shared that. Whoops, haha. I shared a window instead of a screen. Okay, there we go. This
okay, now we can see something. Good. Thank you.
Okay, please do let me know again if it becomes a problem. So here we go. Let me go back. So I created a new model by right-clicking here, adding new model, and then it brings me to here. And if I want to create a new latent model, then this is very easy compared to a lot of software. All I have to do is go find the items I want. So let me go find some items over here. How about, efficacy, 1 through 10. And I just select them and drag them out. And there we go. It creates that for me, which is so nice. Here's ease of use. Let me just drag that out. And let's do a couple more. Enjoyment. And, playful. Let's put it over here. And let's do skill acquisition as our outcome variable. Okay. So we have all these variables, and we can just move them around as we desire. We can change the orientation of their indicators as shown before, and we can play with this. So I'm going to just structure this real quick. Let's just make up some theory off the top of our heads. Let's say that efficacy and ease of use make a software more enjoyable, and so I'm going to play with it more. Let's see. Pull that down there, and because I play with it more and I enjoy it, I'm going to gain more skill from using it. Let's pretend. So just throw that together. And then what you can do is you can connect everything with regression lines here. So click and drag, click and drag. Notice as soon as I predict something, it produces a residual, an error term, because everything predicted needs residual. Also, my guess is there is a relationship between playful and enjoyment. I'm going to leave that out for a moment just to show you the effect on model fit, but then we'll add that later. Also, I can add correlations right there. And I can add a couple more lines here, probably like that. And I haven't added lines from efficacy to skill acquisition or ease of use to skill acquisition. I'll show you what that does in a moment to model fit. Let me just clean things up a little bit so I can zoom in. There we go, and pull that in. There we go. And now I can zoom in a bit. Okay, so we have a structural model here. That is a causal latent model. And I can run this just as I ran it before. Just keep the defaults. And it comes up with these estimates. Let me zoom in a little bit. There we go. And as before, it is using unstandardized values here. So I'd like to see the standardized values. So down on the bottom left, in the outer model, give me standardized. In the inner model, show me everything. In the inner model over here, standardized. And everything else is how I like it for now. And now we have all of our standardized estimates. One nice thing about Smart PLS is if you have overlapping estimates like this, you can just click and drag so that they are in a place that is easier to read. And if we want to see which paths are strong, we can even include some highlights. You see on the bottom left here, if I use relative values, and I should ignore those hidden paths there, but you can see this path right here is highlighted a bit. 427 is a pretty strong value. This one's highlighted a bit, and this one's highlighted a bit, just thickened, but I'm going to get rid of those highlights. There we go. All right, so in the structural model, you can still evaluate the measurement model, this outer model, but we're not going to. What we're going to do is look at all the other stuff. So we can, over here on the left, look at things like R square. Zoom out. Here is the R square for all of the endogenous or predicted outcome variables in our model. For those not familiar with R square, it is the variance explained in that outcome by all of its predictors. And anything above, well, depends on context, but in social sciences like this, anything above 0.2 is considered, worthy of paying attention to. Above 0.15 is probably there's something there. Above 0.1, it's pretty weak, but maybe there's something there. Less than 0.1, there's not a lot going on. So we have some decent R squares here. which is nice. And let's go back to the graphical. And then everything else is as you would expect from an SEM model. These estimates are regression weights. They are the extent to which one variable affects another variable. If you were to hover over a variable, you get its information, just as we did before. The only change here is since we have prediction going on, you get an R-square value. And now let's check out model fit real quick. Notice our model fit is not fabulous. A lot of red there. The CFI is close to 0.9. Above 0.9 is supposedly fine, but it would be nice to have it a little higher, especially since we see all this red over here, including the SRMR, which we'd really like to be less than 0.05. So without modification indices, we don't know for sure which estimates we're missing that we shouldn't be missing, but we can take a pretty good guess. So we have, as I said before, enjoyment and playfulness are probably related, but we didn't include that. So take note, we have a model fit, let's see, our SRMR is 0.085. Let's remember that, 0.085. And I go back over here, I'm going to add a line between enjoyment and playfulness. Let's see, I think the more I enjoy it, the more I'll play. The more I play, the more I'll enjoy. It could go either way. But I've added this one. I'm going to run this again. Run all the defaults. And notice that effect is indeed fairly large, 0.421. So missing that was not intentionally hiding information, but it was statistically hiding information, which affects the rest of our model. The estimates over here will have changed because of this new prediction. And if we look at our model fit, look, our SRMR, 0.056, way better. Now, there may be other things. My guess is that efficacy adds to skill acquisition and ease of use affects skill acquisition. So I'm going to add those and see how that affects our model. Now, ideally, you don't just add lines, just ad hoc like this. You would have a theory behind all of this. And turns out I was wrong with these two. Notice 0.004 and 0.082. Those are probably not statistically significant. And so I was wrong with those. If I was adding them ad hoc, I would delete them at this point because they're not going to really contribute to model fit. If we go over here, look, the model fit didn't really improve. The TLI bumped up over 0.9, but no big deal. So again, if I just added those ad hoc, I'd probably remove those at this point if it was just exploratory. Now, what if we want to see if those paths are actually significant, statistically significant, have a reduction of error sufficient to be confident in their effect? What I would do is a bootstrap estimation instead of just the regular algorithm. So here's the bootstrap estimation. There are several options here. You can pick what you want. Usually bootstrapping, you do more than 500. I'm going to keep it at 500 for the brevity of the workshop, but typically you'd do about 2,000 to 500, somewhere in there. You can do one or two-tailed p-value testing. You can change the alpha level, the significance level. You can change the confidence interval method, which you can use a bias-corrected confidence interval, which is supposed to be a little bit better, does take longer. But if I were doing this on my own, for my own research, I would probably use this bias-corrected and accelerated bootstrapping. So for now, I'll just keep it all the defaults. This does take a moment because it's wrangling a covariance matrix. So bootstrapping in PLS is actually very fast because it doesn't have to wrestle with a covariance matrix, which is very big. But covariance-based obviously does. Okay, now we see the p-values here. What I can do is down on the bottom left, I can change this to not just show p-values, but to show outer weights and p-values standardized, which is what you would typically see in a model. It's the standardized path coefficients and p-values, what you would typically see. And here we are. Let me zoom in. And now we can see the p-values and the standardized regression weights on the model, which is great. Pull that down, pull that up. Okay, so we can see that this 0.42 is statistically significant. The p-value is less than 0.001. If I wanted to know how many zeros were there, you could over here in SmartPLS preferences change the decimal places, apply, and you can see all those p-values there, all those decimal places. I think that's kind of hard to read though, so I'm going to fix that. Go back. There we go. Okay. We can see this path from efficacy to enjoyment, there is no significant effect. And we can see that the effect from playfulness to skill acquisition, there is no effect. So the more you play with software, doesn't mean you're going to get better at it, but the more you enjoy it, the more you'll get better at it. This p-value is statistically significant. So that is structural modeling. You can also, in the covariance-based side, look at the specific indirect effects, which is cool. These are the indirect effects implied by your model, whether theorized or not. And it includes serial indirect effects, which is really nice. So does enjoyment mediate the effect from ease of use to playfulness? We can go look over here at the p-value, and the answer is yes, it does. Here are all the other p-values. Looks like there's only one other mediation going on in our model, and that's that enjoyment mediates from ease of use to skill acquisition. The serial mediation in our model does not pan out. It is not significant. So that's pretty nice. It does all possible specific indirect effects. And if you want the confidence intervals on that, including bias-corrected confidence intervals, it does provide that. It also provides total effects, which some like you to report. Yeah. I don't think if there's anything else in that. Yeah. Anyway, super easy to use. Drag and drop and reports are generated for you. I guess I should show you, if you wanted to output that report, let me go back to open that report. Let's say I wanted to take this over to Excel or something like that. I could just click on the copy to Excel button right here. I don't know if you can see that, gray on gray, but there's a copy to Excel button. So let me click on that and open up Excel. And stick that in here, paste, there it is, copy it over to Excel. So that's pretty nice. Okay, let me open this up here. Let's see, just want to make sure I'm not missing anything. Good. Somebody asked, Professor Gaskin, we are seeing still HTMT. Oh, that was earlier. Okay. So that's structural modeling. There are a few other things I would love to show you. Let me just make sure I haven't missed anything here. Oh yeah, that one. I want to show you this. Let me save this, go back, and create a new model. Just a CBSEM model. I'll just call this zoom in DIY. That's do it yourself. And instead of, oh no, I did show you that. Yeah, I showed you how to build a model. My bad. Okay, let me go back and make sure I haven't missed anything else here. Oh, that I should show you that. Okay. You can in this, you can create higher order constructs if you want. It is not yet optimized for higher order constructs, and there are lots of more steps you have to take to make them work. But let me show you how that works. So let's say we have this model, and I'm going to simplify this model for a sec just to make life easier. Get rid of that, get rid of that. And I'll keep those, keep that, and yeah, get rid of that. Okay, I'm just simplifying things for the sake of this exercise. There we go. So let's say I thought that decision quality and information acquisition were really part of the same higher order factor. I could create a higher order factor by deleting these covariance arrows here between these items and other items, these factors and the other factors. And then I could add a new latent factor right here. And I'll call this HOC for now, higher order construct. Really, you'd have a better name for that, but I'm just messing around now. If I click connect, I can connect this to this, this to this, and then I can covary this to this, and this to this. And notice this is still orange, which means it's not ready to run. And the reason it's not ready to run is because it's missing a constraint on one of these paths. So I can double click one of these paths and add a constraint of 1, hit apply, and now it's ready to run. Notice here, I don't have to use a repeated indicator approach. For those who are familiar with PLS, you may recall that you're supposed to use repeated indicators whenever you have a higher order construct. Not necessary in covariance-based. Sort of. It actually depends on if you want to validate them fully, then you have to. But anyway, here we go. So I can run this now. I can run the basic algorithm, run that, and change this to standardized and intermodal standardized. There we go. And let me zoom in. And we can see that these two loadings, these are just like the loadings over here. These two loadings are pretty good and imply that this higher order construct, whatever it is, has some validity. The AVE on this is going to be above 0.5. The composite reliability is going to be above 0.7 because these values average out above 0.7. So that's how you would quickly do a higher order construct. If you want to do it fully, let me show you some other things here. Notice if I hover over this, I have to zoom in. Go over here. Okay, if I hover over this, the composite reliability, the Cronbach's alpha, the AVE are all 0. And the reason they're 0 is because SmartPLS hasn't fixed this yet. It has no indicators. It thinks it has no indicators. And so mathematically, there's nothing there. So you'd have to calculate those manually, unfortunately, or you'd have to go over here. And I'm going to go a little bit fast here. This is sort of an advanced feature. Most of you, this isn't going to be relevant. But for some of you who are like, this might be very useful. You can go over here to factor scores, and you could copy this, this table of factor scores over to Excel, save it as a new data set. I should just do it. Let me just do it. I'm going to copy this, and I'm going to create a new data set over in Excel. These factor scores, let me explain. Let me save this real quick, and I'll save this into downloads for now. And I'll call this CB-SEM workshop LVS. That's latent variable scores. Save that. Okay, so these latent variable scores, these factor scores, these are the centroid value of the latent factors. That's not going to make sense. Let me go over here. So each of these sets of correlations, zoom in, implies some centroid, some center around which these items are correlated. And that center can be measured directly, calculated, or estimated. And that estimated center is a factor score, which is based on sort of the weighted average. Oh, that's a terrible way to say it, but something like the weighted average of these indicator loadings. Again, I'm grossly oversimplifying, but more or less that's what it is. And so you can create a single score for this latent variable. Instead of using these 7 items here, we can just have one variable to measure playfulness. So that's what the factor score is. And now I have a factor score for this HOC, this higher order construct. At least I hope I do. Let's double check. What I'll do is I'm going to add, let me save this. Let me add a new data set here by right-clicking here and new data set, import data file. Let me go grab that from downloads right there. And it says, here are my variables. Notice it only has these variables now. It doesn't have all that other stuff. It just has one variable for each latent factor that we had in that model. And that is fine. That's what I want. I don't want the case index, though. I can uncheck that, import. And we can look at all that. I showed you that before. I'm going to go back and go back to a new model. So create a new CB-SEM model. And we'll call this path. And change the data set. We haven't done this yet. So over here, we're still on the original data set. I'm going to click on this and switch over to this LVS data set. And I can now pull out each one of these. Ooh, yes, enter. Ooh, sorry, let me zoom out. I can pull out each one of these and use it as its own factor. And I can use these now in a path model. So I could draw these however I want. I don't need information acquisition actually, because that's in the higher order construct. There we go. I can relate these guys. Let me hide all of this. Control A, hide indicators. There we go. And now I could connect these in a causal model like this if I wanted. There we go. And now I can use this higher order construct as its own factor. Run this and it runs just the same as before. There they are. Path coefficient standardized. There we are. And let me zoom in. Whoop. You can see that they operate just as they did before. So that's how you use a higher order construct. I didn't actually show you how to validate it. Ooh, I don't think you can in the covariance-based side because you can't export the entire model. Oh, you could actually. It's complicated. For those who are keen, I'm not going to show you every step, but I'm going to talk you through it real quick. If you wanted, you could in the previous model. Let me save this. This one. Yep. You could over in the factor scores. If I run this real quick, you could grab the factor scores for that column, the column for decision quality and information acquisition, and save those as two new columns in your other data set, your original data set, and then use those as the indicators for a new HOC factor in your measurement model. Essentially bringing it back down to a first order where the indicators are the dimensions from the second order. Sorry, if that didn't make any sense, don't worry about it. That was sort of an advanced feature. Okay, but that's how you would do it. Let me see if I have other things here. That one, oh, that. Let me show you this. Let me go back to this model. I'm going to delete this and delete this. Okay, we have now a measurement model with no covariance arrows. And it turns out this model runs just fine. You don't need those covariance arrows if you check the box over here. There is a box right here that says imply latent variable correlations. If you have no correlation arrows in your model and you don't want to draw them because it makes it messy. Right now it's a fairly small model, but you remember before we had that big model, and maybe it didn't all fit on the canvas. So if we wanted to just throw all of our variables in here and have a mess, but not have too much of a mess, we could just not include any correlations and then just imply the correlations instead. And it will calculate them all without having to draw them all. So if I run this, we can actually see still the correlation matrix. If I go over here to latent variables correlations, notice it still produces the correlation matrix, even though we haven't specified any correlations. And it includes those correlations in the specified model when you're assessing model fit. So it's still all there. You can still assess things like discriminant validity, even though we don't have any correlations specified visually. They are specified under the hood. So that's a little feature that's kind of cool. So this is the same model as if we drew all the covariances and then unchecked that checkbox. Let's see. Oh, I want to show you this. I want to show you how you can compare this model to a model in Smart PLS in the PLS side. So let me create a model real quick out of this. In fact, I probably have a model over here, structural. There it is. Here's this model right here. And if I run this, just to get some estimates real quick, I'm going to save this model output. So right now we're in the output section. There's also a modeling section. We're in the output section. We can save this output as a report. So I'm going to click Save, name this as CBSEM structural. That's actually great, just like that. And it's going to save into this folder, Create. And then I can go back and convert this model. Check this out. This is so cool. I can convert this model to a PLS model. So it'll run in the PLS algorithm. So let me click on that. And it asks me, what type of model do you want? A process model or a PLS SEM model? And I'm going to use PLS. And I'm going to name it PLS SEM structural model. There we go. Save that. And notice it automatically converted the whole thing over to the PLS side. It got rid of the error residuals. It got rid of all the residuals on the indicators. It got rid of the covariance between ease of use and efficacy. And this is a PLS model now. And I can run this with a regular PLS algorithm. I should show you real quick. Notice now when I hit calculate, there's a ton of stuff you can do. And so that's the PLS side, which they've built out over 2 decades. They will continue to build out the covariance-based side until it is this fully featured. It'll just take them some time. But here we go, PLS algorithm. I'm going to just use the defaults and hit start and zoom out. Here are those estimates. And if I wanted, I could now compare this model to the one we just created in CBSEM. Here we go. Here are the 2 models right here. Let me pull that over this way. So PLS on the left, covariance-based on the right, and let me zoom in so we can see it all. I can adjust it just like I would before. Let me adjust this real quick. And we can see how these differ. So the R square for skill acquisition, 134. R square for skill acquisition, 156. Pretty close. We can look at the Cronbach's alpha, 846. And over here, the Cronbach's alpha, 846. They are the same. We can look at the indicator estimates. So 852, 817, and these are showing unstandardized. Let me show standardized real quick. Let's see, outer model standardized and inner model standardized. There we go. And all that works. Okay, here we go. Back up to here. 835 and 781, 852 and 817. So they're similar, but not identical. It is a different algorithm running, and so they will differ, but they should be fairly consistent. We can see the paths that are probably not significant. This 0.075, 0.082. Over here, 0.081, 0.099, similar. Yeah, so this is how you would compare them. And you can actually do quite a bit more with this compare, which is really cool. If you go up here to select detail, look at all these things you can compare across these 2 models. So for example, if I wanted to compare, let's see, discriminant validity, measurement stuff's going to be about the same, but we'll see it. Here's Fornell-Larker. Let me go over here, discriminant validity, Fornell-Larker, and you can see these estimates are pretty close, 0.544, 0.541. You can see these values on the diagonal are fairly similar. But yeah, you can compare them across anything you want, as long as it was produced in that estimation. Here's a notable exception, model fit. It produces just these few things in the PLS side, and model fit for CBSEM obviously produces a lot more. And so you can't really do apples to apples comparison here. But for nearly everything else, you can. Indirect effects. Ooh, specific indirect effects. Indirect. Oh, I need to run the bootstrap to do that for covariance-based. So it won't see those. Oh, it did. It did all of them. Sweet. And they're more or less the same. Isn't that cool? That's so cool. You can compare models, even covariance-based CBSEM. There's some other really cool stuff you can do with compare models. There's, let me show you real quick. Let's see, go back. There is in the PLS side here, you can actually do a model comparison, and it will do like a how different are these two models, and you could do different dependent variables or different independent variables, or a higher order construct versus a lower order construct model. It's really cool. You can do all sorts of model comparisons in PLS. Okay, let me just make sure I haven't missed any questions here. Nope, we're good there. Now let me go back to my list. Oh, sweet, I got through that. Nice. Okay. I have shown you pretty much everything that is currently featured in covariance-based Smart PLS. That is all the features they have currently on that side. There are some really cool things you can do in the not covariance-based side that, if you want, I can spend a few minutes on. Or if we'd like to just take questions, I can answer just questions from here till the end. Ahmad, Vildan, what do you think? Should we just show some more features or take questions at this point?
I think we can talk about some more features if you wish.
Sure. Now, from here forward,
I have actually, sorry, I try to summarize all questions. I'm going to ask you one by one. So still
great.
we have time, I think, yeah.
Then I'll be brief.
Maybe we can, great.
I'll take maybe another 15 minutes then and show you some really cool features of Smart PLS that I haven't shown you yet. And I haven't prepped any of that. It's just, I'm just making things up at this point. But there's some really cool stuff that you shouldn't miss. If you've never used Smart PLS before, but you've used Amos or Lizral or M+ or Stata or SAS or any of those other EQS, JASP, whatever, JASP, Smart PLS is really cool. So let me show you a few things. So, and I'll just take another, 15 minutes and then we'll go to questions. So this is the PLS side of Smart PLS. It has way more features. You can do all sorts of crazy stuff here. And I'm trying to figure out where I want to start with that. A few things. So first off, you can create formative factors, which we would not do in a covariance-based environment. To create a formative factor, let's say my ease of use, we're just going to pretend for a moment, ease of use was formatively measured. We could right-click this and invert the measurement model. Sorry, that's really small. We could right-click any factor and invert it. And that would change these arrows to point at ease of use, implying that these indicators are not required to be correlated. They're just together a summation of what ease of use is. They form ease of use instead of their reflections of ease of use. And the way I measured it in the survey, actually, this is not true, but just for the purposes of this exercise, I can show you this. It runs just the same. If I run all the estimates, it still runs just the same. It operates just the same. There are some nuances to doing this if you have an endogenous factor being predicted that way. But more or less, that's how you do it. You just right-click it and invert that measurement model, which is kind of easy, which is nice. In the PLS side here, let me run this one more time, start calculation. You can see over here in the output, we get a few things we don't get in the covariance-based side. One thing is the F-square. So F-square is or pseudo F is the effect size. It's the size of the effect one variable has on another variable, its impact. And anything green here is considered good, anything red is considered no good, anything black is considered modest, not really helpful, but not really nothing. There's maybe something there. So it looks like enjoyment has a fairly decent effect on playfulness. Or maybe it's the other way around, I can't remember. Let's see, we have the arrow going from enjoy to play. Yeah, there we go. So let me go back to this. Here we go. I was showing you matrix view before. This is a little easier to read, the list view. So we can see which effects are the strongest. We can sort it, which is nice. And we see this is the strongest effect. We don't get that in covariance-based yet. There is a way to calculate it, but the software doesn't do it yet. If we look over at the collinearity statistics on the left, this is something else we don't get. in the covariance-based side yet. It will be coming. But we can look at the inner model list. Collinearity is referring to the multi-collinearity, the redundancy of predictors, meaning for example, if I go over here, is efficacy predicting the same variance in playfulness that ease of use is predicting in playfulness? Are they redundant with each other? And so let me go back down here to this list. The answer is no. They are, well, this actually doesn't show that, but you want values here less than 3.3. And so we see they're all green. We have good collinearity. It's not highly multi-collinear. You can also see that for the outer model, which everything's reflective in our model, so it doesn't matter. Let's see, other things that are different here is if I bootstrap. Let me go back to the bootstrapping. Run a bootstrap, and notice on this one I have 5,000 subsamples requested, and whereas with the CBSEM I had 500. Look how fast this is. Boom, done. Yeah, PLS bootstrapping is really fast. And we can get some cool things with the bootstrapping. We can get the specific indirect effects with p-values, which is very nice. All the way over here. Here are the p-values, and we can get. I think that's all for that. Let me show you a really cool feature. You're gonna love this. Check this out. I can connect a latent factor to another arrow, and that is a moderation happening. Isn't that cool? I'm gonna do it over here where you can see it a little bit better. So this I'm implying here that ease of use strengthens the effect enjoyment has on playfulness. So if it's easier to use, then if I'm enjoying it, I'm going to play with it even more. Or maybe ease of use has a moderating effect on the relationship between enjoyment and skill acquisition. So as I enjoy it, I'm going to learn stuff, but I'm going to learn even more if it's easy to use and I'm enjoying it. So these imply interactions, and SmartPLS just calculates those automatically. So I can just run this, nothing changed, and I get something new here. The simple slopes plot. Let me show you over here. Simple slopes plot. And this calculates the interaction. And so here's the default, the ease of use times enjoyment. There's not much going on there. I should have picked a better moderator. But what this says is at the average, blue, at the average of the moderator, what is the relationship between enjoyment and skill acquisition? And then if you were to take away, do a low value of the moderator in red, what would that relationship be? And if you were to do a high value of the moderator, what would that relationship be? And so if you see diverging or converging lines here instead of parallel lines, then you'd say, yeah, there's some moderation going on. But there's a way to visualize it, which is really cool. And then you can also add quadratic effects. So I can add a quadratic effect to, let's see, it's going to put that over there. Here we go. I've added a quadratic effect there. I need to get rid of these interactions while I'm estimating a quadratic over there. So this implies that the effect that enjoyment has on skill acquisition is not linear. It's curvilinear. So this is a curvilinear estimation, which is really cool. Let me add another quadratic somewhere else just for fun. Let's see, how about I add a quadratic? Let's see, ease of use, playful, efficacy to enjoyment. I think this one. Let's try that right there. Okay. So again, I'm implying a curved relationship here. And I can run this standard algorithm, start that. And we can see these estimates. And you probably can't see those estimates. That's very small. Here we go. And they're fairly small, but we would expect a curved estimate to be not terribly big. And we can go view the significance of those if we run a bootstrap. Run it. And go to the output and look at the path coefficients. And here are those quadratics right here. And we can see whether those quadratics are significant. And yes, that one, the effect from enjoyment to skill acquisition is non-linear. It's curvilinear. And if we go up here to enjoyment to skill acquisition, there's also a linear effect. It's both. There's a significant linear and a significant non-linear effect from enjoyment to skill acquisition. That's pretty cool. You can also do a multi-group analysis, which is awesome. Let me take this out. Let me go generate some groups really quick. So if I go to the data set I'm using here, let's see, what data set was I using there? This one right here. I can generate some groups out of this data. Let me zoom in. Let me go down to something obvious. Let's see. Here we go. Here are all our demographics. Let's do something like child order. First child, last child, middle child, one of many, things like that. Okay, let's name this to child order. Who doesn't like that? Okay, I'll leave it as the default for now. Hit apply and zoom out. And it automatically detected 4 groups in that variable. And I don't remember what these are off the top of my head. I'm pretty sure it's only child, first of many, middle, last. I'll just name those real quick. Edit. Only child, apply. And then this one, edit. This is first or oldest child, I guess, oldest. Apply. And edit. This is middle. Apply. And this is edit. First, youngest. There we go. Something like that. I might be wrong, but something like that. That's all saved. I can go back to my model, and I can now run a multi-group analysis. So different options here. I'll just do a permutation multi-group analysis. And I can pick the models, the groups. So group A, we're going to say, is the middle child versus group B is the only child, something like that. And I can start the calculations. And it says I have a singularity matrix problem, which means something has 0 variance, which is a problem. Let's see. There's just not sufficient variance. Let me pick 2 different groups and see if that works better. Okay, instead of only child, let's do oldest child. Still doesn't like that. Let's go back to the setup. Youngest child. Must be on the middle child thing. Let's see. Oldest versus youngest. There we go. Now it's running. Okay. The reason I was getting that error is because there's something curious about middle children, I guess, where they exhibit 0 variance on one of these items. But now we have these results run for 2 different groups. If you see down here at the bottom, there is a group option here. And now watch in the top right of my screen here. If I switch it, these estimates switch. And I can just toggle back and forth between these. And if I zoom out, oops, by the way, you can see the whole model actually toggles back and forth. And I can look at all sorts of curious things, including the differences between these models. If I go to path coefficients, here are the path coefficients for oldest child. Oops, shouldn't click on. There we go. For oldest child and for youngest child, and the difference between them, and whether that difference is statistically significant. That's pretty cool. And there's a bunch of other stuff I can do there, and I'm eating up all the time. But there's more and more and more and more. So many cool things you can do. The very last thing I'm just going to tell you about, not really show you, is you can create a process model. Here's process. Some of you have used the process macro in SPSS. The cool thing about the process emulator in SmartPLS is that it can use latent factors. Process in SPSS only uses composites, single variables to represent each construct. Whereas the emulator in SmartPLS can use latent factors, and you can add quadratics, and you can add interactions and multi-group analysis and control variables all at the same time. You can have, whereas in SPSS, there's a fixed set of models you can create, like 16 models or something. In SmartPLS, the model can be anything. You can create any kind of a model with any number of variables, all latent if you want. And it can emulate the process macro like that. Anyway, I'll stop there. And then if there are questions, I think Ahmad's been compiling some questions. I can answer those.
Thank you so much, Professor Gaskin, for this great presentation. Actually, we have a couple of questions. I did my best to just group them. I hope we have enough time to ask all the questions. I will start outside from SmartPLS. We have a group of attendees. They're asking about, is it necessary to do EFA before we go to SmartPLS or explanatory factor analysis? Do we need to do it before we do a confirmatory factor analysis for validity, convergent validity, and other things? So this is the first question. We can start with it.
Yeah, good question. Here, I'll stop sharing for a sec. So yeah, good question. I get this question all the time. Is the EFA, the exploratory factor analysis, necessary? And the answer is usually not. Usually you don't need to explore the structure of your measurement model. Usually you know it, you theorized it. You didn't just come across a survey with a bunch of random items. Usually you know that these 5 items belong to this construct and those 7 items belong to that construct. And so an EFA isn't necessary usually. The times when it is helpful is if you have secondary data. For example, let's say you have a large survey from a secondary source. I did one with the World Bank once. They had like a 50-page survey, and it was just all these variables. And so an EFA was very useful to consolidate that and do what EFA is good at, which is dimension reduction. I was really good at reducing the dimensionality of my data set. The other time it's really helpful, though some would say still not necessary, I find it very helpful, is if you are facing discriminant validity problems. The CFA is a little bit difficult to detect discriminant validity problems and fix them because it is constrained. You're guiding it. You're saying these items belong to this factor. But what if they don't? Well, there's no way to detect that, except that your model fit is bad and your validities are bad, but it doesn't tell you how to fix it. Whereas an EFA, because it's unguided, because it's just exploratory, it will surface those issues right to the top. You'll see that these 5 items don't go with those 3 items, and they go over here with this factor instead. And it just happens. Whereas in a CFA, you hide that information and you can't detect it. Now, there's actually a way. Let me show you super quick. In the PLS side, let's see, share that screen. In the PLS side, if I open this back up, where'd you go? Right here. And if I calculate real quick, PLS algorithm, yes. There is in the latent variables not there. It's probably in outer loading. So wait, where'd you go? Here it is. There is a pattern matrix. There's actually it's down to discriminant validity. That's where it is. Cross-loadings matrix. There's a cross-loadings matrix in PLS, which shows you all of the loadings from another factor. So let's say we didn't have discriminant validity between 2 of these factors. We could go look at the loadings, for example, for skill acquisition, and compare them to all the loadings over here and see if there's like a really strong cross-loading. Now, I don't actually see one here. I might see one on enjoyment, though. Let's see, here's enjoyment. Those are very strong primary loadings, and it looks like, we don't have many strong secondary loadings. But if we did, that would be an indication of where we could look to fix our discriminant validity problem, is in this EFA. This is an EFA in SmartPLS, which is kind of cool.
Thank you. Yeah, that's great. Thank you so much. Then we have a question about, I think the distinct things in covariance-based structure question modeling is the modification indexes. Now we have a question, or actually a couple of questions related to this one. What if we have a problem with the modification indexes in Smart PLS 4? Do we have a way to enhance the indexes
Yes.
with the current version? Yeah.
Yes, let me show you. So if I go back to not this model because it's PLS, let me go to CBSEM. So let's say I'm in this model. Can you see my
screen is not
screen?
shared? Yeah, yeah.
Oh.
Also, your cam is off, Gus.
Uh-oh. Okay, I stopped sharing again. Let me share again.
Yeah, that should work.
There we go. Okay.
Okay.
Yeah?
I think
Okay,
it's
you can
still
see my
loading.
screen?
It's still loading, maybe.
Oh, okay.
We're still not able to see.
Oh, no. Huh. All right. Microsoft Teams. Let's see. Not sure what to do about that. Let me, maybe I'll just share this screen itself. Share. Ooh, not that one. Let's see. How do I, it doesn't want to do that. Try that. There we go. How about now?
I think it's still not visible.
Well, then I'll just have to talk about it vividly. Okay, so if you wanted to simulate having modification indices in PLS, because currently there is no modification index report, what you would do is create a just identified model. A just identified model is a model where every parameter is specified. So in the model we were looking at before, I would connect every latent variable to every other latent variable. I would have every possible drawn arrow drawn. And then that would give me a saturated model. And so it is, by definition, the best model fit I can get. And then if I want, I can back off from that by deleting non-significant paths that are also non-theorized paths. And then that would essentially do the same thing as working in reverse with modification indices. I would be taking away paths instead of adding paths. And then as long as I still have good model fit, my model is good enough. I would hesitate to ever delete a path that was theorized. So if I had a hypothesis about a path, even if it wasn't statistically significant, I would still include it, just to not hide information. But if it was a path that I had added post hoc, just exploratory to adjust model fit, if it was non-significant, I wouldn't feel bad about deleting it, especially if it also didn't affect my model fit adversely. So there's that. Sorry I couldn't show that, but that is how you do it.
That's great answer. We can't see your camera. I think your camera is off.
Still can't see me. Oh,
Maybe just only me. I'm not able to see. I will move to the second question. Actually, one of the good things at the feature in partially square lattice SEM that most of academic or research are preferring to use it because of it accept the low sample size. Yeah, your screen and your cam is okay now. So what about, great. Yeah, what about covariance-based structure question modeling? What is the minimum, let we say, sample size required, or is there any formula for calculating the sample size that it's enough to make some conclusion?
Yeah, that is a big difference between the PLS algorithm and the covariance-based algorithms, is sample size requirements. So for PLS, sample size requirements are fairly low because it's not trying to work around a covariance matrix. A covariance matrix is huge. It's every possible correlation covariance between every single variable in the model. It's huge. And it's hard to deal with. And anytime you increase the complexity of a model, you have to increase the sample size in order to reduce error sufficiently to be confident in any estimates that are produced. Now in PLS, it is not trying to wrestle a covariance matrix. It's dealing with regressions, fairly simple linear regressions. And so the complexity of the model isn't based on the number of variables total in the model. It's based on the number of predictions. And so as long as you don't have 50 predictions on a variable, then it's not that complicated, and you can handle those predictions, those regressions, with much lower sample size. And so the rule of thumb, this is very rough, and there are actually good calculators out there to do this, and it's very context dependent and idiosyncratic. But if you were just looking for a basic rule of thumb, they say that you should have anywhere from 5 to 20 times the number of predictions for a single endogenous factor. So you can see my screen now again, I think.
Yeah, it's visible now.
So the factor here that has the most predictions going into it is playful. It has 3 going into it. So I'd need 5 to 20 times that for my sample size. So far, we're being very liberal. 20 times 3 is 60, right? And so I need 60 sample size to run this model. Now with covariance-based methods, it's not based on those regression arrows. It's based on the number of indicators included. So in this model, I have 9 plus 8 is 17, plus 7 is 24, plus 4 is 28, plus 7 is 35. I have 35 indicators included in this model. And I, again, need 5 to 20 times that. Again, very rough. There are better ways to calculate this, but 5 to 20. Let's say I'm being very conservative and I just want to do 5. Well, 5 times 30, whatever it was, 34, is a lot more than 60. Yeah, it's 180-ish. So I need at least like 180 to calculate this model. Yeah, in a covariance-based side. Yeah.
Thank you so much. Since your screen is actually visible, we have a question about control variables. How can we deal with control variable in CB, covariance-based structure question modeling?
Yeah, so the way you deal with control variables, whether it's in CB, SEM, or PLS SEM, is you just treat it like another independent variable. So let's say I wanted to control for, I have some demographics down here. Let me control for age, for example. I would pull age out here, and there's age. I'm just going to hide that real quick, hide indicators, and I would connect it to all endogenous factors. And if I'm being prudent, I would also covary it with all exogenous factors. And so now it is fully controlled for, and I can just keep it back here and run this as I would. Now, if you want to really do a good controls, confounds estimation in Smart PLS, the way to do it is in the process macro, or the regression, the regression modeling. It does controls very well and actually separates them. But that works.
Yeah.
Yeah, so it just produces estimates as if it were another independent variable, but then you just report it. Here's age right here. You just report these as control effects, not as independent variable effects.
I think your screen's frozen.
Well, okay, so just hear my words, I guess.
Yeah, it's fine. Yeah.
Yeah.
Go on,
I don't know why it keeps doing that. I don't know.
Yeah.
Okay. Well, yeah, you just treat it like another independent variable. That's all. And then when you report it, you report it as a control.
Thank you so much. Then we have another great question actually asking about, now I think the recent version of Smart PLS, they add process for moderation, mediation, or conditional indirect effects. So one of the participants asking about which one is better to use. Is it to use the macro process highest in SPSS or using in Smart PLS4? So, and then actually they're also asking about, this is a related question about how we do the indirect effect, or which is like we can say mediation effect in Smart PLS when we dealing with covariance-based structure question modeling. So this is kind of related questions.
You still can't see my model?
Yeah, I can see a window. Yeah, pop-up window. Yeah, it's not, process is open.
Yeah, so here's the process model. I just converted my PLS model to my process model, or maybe I converted the CBSEM, I can't remember, but it auto converts, which is really nice. And yes, you can include things like moderated paths, interactions here. I can just drag from age to any other arrow, and it creates an interaction effect. I can add quadratics. I can add specific moderating effects. I can add mediation's already implied, but check this out. If I add one more here, let's see. Oop. If I add age to this one, we're going to have a moderated mediation, a conditional indirect effect. So if I run this, here's path analysis, start. We can see over here on the left, let me zoom in. Whoop. Here we go, conditional indirect effects right here. And it will calculate these conditional indirect effects. Zoom out again, sorry. Which
yeah,
is...
I think the screen again frozen, sorry.
All right.
Yeah, we're still seeing the process model.
Oh, that's too bad. Well, it calculates conditional indirect effects, moderated mediation, mediated moderation, moderated moderation. It calculates all of those things. And to answer the second question, which should you use? Should you use the SPSS macro or should you use the Smart PLS emulator? And I would 100% use the Smart PLS emulator because it can handle latent factors and you can use any model configuration you want. You don't have to use a specific model configuration. You can just make it anything you want. And it's drag and drop, and it's just so easy. And the analysis output is already formatted for you. And I've seen the process output. Way to go, Dave, for making it readable, but it is a lot of output, and it's not organized in a way that you can, it's not formatted in a way that you can just copy and paste it very easily. So whereas in Smart PLS, you can just copy and paste the output and it's done.
Thank you so much. Actually, we have one more great question we just received. It is about VIF or VIF.
Yeah.
Actually,
Yeah,
there's a paper, I was reading it 1 week ago that I think recently published, it talking about that there is no need to use VIF. It's kind of needless analysis. It was make a big buzz actually in the academia. And so we have a question here about from unknown user. I can't read his name.
That's all right.
So some researcher claimed that VIF is worthless. What is your take on this, Prof? I think he's mentioning that paper.
Sure. I haven't read that paper. VIFs I have not found to be terribly useful, particularly in the context of PLS and method bias assessment. There are some real issues there with trying to use VIFs as an indication of method bias. It's very loose reasoning there. Have I ever used VIFs to omit a predictor? No. The thing is, the VIF would have to be so high that you would see evidence of the multicollinearity elsewhere. You would see strong discriminant validity issues. You would see strong correlations, stronger than you should see. And so all of those things would already indicate that there's a redundant predictor. And so the VIF, it's not harmful, it's just redundant, which is really cool meta argument against VIFs, because VIFs are supposed to identify redundancy, and yet they are redundant themselves.
Yeah, that's my great sense. So we have another question. There are actually many questions related to moderation. How can we do moderation analysis in Smart PLS? So I don't know if we have time to show it.
I showed it briefly.
Yeah, actually we show it briefly. Yeah, please go on.
Yeah, so I showed it earlier in the PLS model. You can just draw a line. I don't know if you can still see my screen, but you can just draw a line from one latent factor to another line, and that creates a moderation, just like that. And then it creates a simple slopes plot. Let me run this. It creates a simple slopes plot here, which shows you that moderation. So that's how you do moderation. If you want to do multi-group analysis, you can create those groups a priori, like we did with the child order, and then you can do either. Oops, I don't know if you can see my screen again. I just changed it. Oops.
Yeah, it's again frozen. Yeah, I think it's again frozen.
Okay, let me get rid of that. I think it's the zooming tool I'm using. Anyway, but if you did a bootstrap multigroup analysis or a permutation multigroup analysis in PLS, that's how you would do it. In CBSEM, there's not currently a method for multigroup analysis. you'd have to create two separate models with two different data sets, each data set for the separate group, and then you could do a model comparison across those two saved reports. Yeah.
Yeah. Thank you, James. I think here's the critical question. One very good question came from participant is that, is it reliable at the moment to use covariant-based structure question modeling using smart PLS and publish the paper? Will the reviewers question that we use smart PLS for? Because we know that CB-SEM is still in the beta version. So what's your answer, James?
I have not yet seen a paper published with the covariance-based methods in SmartPLS, but it's still new. So I mean, the publishing process takes a long time. My guess is, and this is just me guessing, is that Christian Ringel and the others in that team, they're in the process of publishing papers that show that there is validity to using the CBSEM portion of SmartPLS. I haven't seen those publications yet, but I'm sure they're forthcoming. And the only warning I've seen, red flag I've seen in the CBSEM side of SmartPLS is the reporting of the CFI. The CFI estimation seems to be a little bit inflated. If I compare it to Amos, my guess is it would be highly inflated. So there's still some kinks they're working out, some errors they're still working out, but it will not be long. Yeah. What I typically do is I'll do all of my exploratory stuff in SPSS, like an EFA, and then I'll do all my confirmatory stuff in PLS, and that works very well.
Thank you so much, Prof. James. I don't know if we have time. We just run.
I could probably take one more. I have to run across campus.
Let me take one. Yeah. So
Yeah,
let me take the
it's a big
final
campus.
question. We didn't touch higher order construct. So
Not too much.
I don't know if, I think this need a lot of time explanation. I don't know, maybe we can just like briefly talk about how, we can do it in.
I have some videos on how to do that on the PLS side. On the CBSEM side, it's a multi-step process, which we covered briefly. I don't know if you could see my screen when I was doing it, but essentially you run the model with a higher order construct in there. Can you see my screen right now?
I can see, the model is visible. I hope it's visible also for the others.
If I look at this one, no, not this one. Whoops.
It's visible. I just get.
Good. I must have gotten rid of it. That's too bad.
Yeah.
Okay. Well, I had a model with a higher order construct in it. You just draw another latent factor and draw the arrows from that latent factor to the lower order dimensions, and then you add a constraint on one of the paths. And then you correlate that higher order construct with whatever it needs to be correlated with it, and then regress it on whatever it needs to be regressed upon. You just treat it like any other factor, and it works in CBSEM. If you want to validate it though, like check its AVE and its composite reliability, that requires several more steps. Currently, they're going to fix it. It's going to be easier, but for now, it requires saving factor scores in your original data set, and then uploading the new data set, and then remodeling it where you don't have the first order dimensions anymore. You replace those first order dimensions with the indicators of their with their factor scores. And then you model the second order factor as a first order factor with the indicators of those first order dimension factor scores. So I don't know if that made sense, but that's how you would do it. It would totally work.
James. That's makes sense. So I will not take more of your time. I think we have 5 minutes extra from the time. So we will stop here. We apologize for not taking more questions. We're sorry for that. We have a couple of other questions.
You guys can always reach out.
Professor James,
I respond to every email.
You can. That's awesome. Actually, he was so fast when I contact him, like in less than 1 hour, I get response from him for this invitation. So you can contact him. I'm sorry, I'm talking about on behalf of you, James. So thank you so much. I respond to every
email within 24 hours usually.
Thank you so much, James, for this great presentation. It was really great honor to have you with us. I hope we can see you in another seminar another time. So I'm going to stop here. Let me see Dr. Vildan.
Thank you for this perfect information you shared with us. Hopefully, see you soon.
Sounds good. Thanks, guys.
Thank you.
Thank
Thank
you.
you all. Thank you all. Thank you, James. We will be.
See you.
See
All
you.
right.